Right. Today we're going to study geodesics on surface of revolution. Surface of revolution. Well, surface of revolution provide, we find many good examples. We can construct surface of revolution with constant Gauss curvature or even mean curvature, right? So we are very interested in how do the geodesics look like, okay? All right, so let's have a quick review about surface erosion. So this is a surface erosion. Okay, here's the axis, y-axis, z-axis. Okay, and the curve, initial curve is here and rotated around the z-axis. So we have a natural parameter, natural surface patch sigma u and v, and f of u cosine v, f of u sine v, and g of u. Okay, this is a curve gamma. We call it meridian. We rotate it around the z-axis. Okay, so this is a gamma. Well, the curve, yeah. For every fixed angle, the curve is a unit speed curve. You get, we assume that f prime u square plus g prime u square equals always equal 1. That means if you look at the partial derivative, right, of this, look at partial derivative, what do you see? Okay, so that is going to be f prime u cosine v, f prime u sine v, and g prime u. Okay, so so then you find out the length of this one is going to be f prime u square plus g prime u square equals 1. So every such curve for fixed v, we call the meridian. Okay, the meridian has a unit speed. So what is the curve here, right? So this is the angle v. So for fixed v, you have a meridian, right? So from here, it's like that. This is a curve we're talking about. Okay, this curve is the same like this curve. You just rotate around the z-axis, right? So if the original curve is unit speed, then this curve, of course, unit speed has a unit speed. Okay. So anyway, so sigma u is tangent to, is a tangent vector to this meridian, and the sigma v is here. Now I want to look at sigma v. Okay, what is the sigma v? Okay, sigma v, that will be fu negative sine v, fu cosine v, and z, right? So the length of sigma v squared, just sigma v, it's going to be f of u. Okay, here f is positive. Okay, we always assume it's a positive. So what is f? You look at and the point here, right? Okay, and the point here. So when v is 0, this is a curve in the xz plane. In the xz plane, the first coordinate is going to be f of u. Second coordinate 0, and third coordinate g of u. So g of u is the height f of u here is a horizontal. Okay, so it's from here. Yeah, g of u. This is g of u. This is f. Hold on. Yeah. Okay. Mm-hmm. So I want to look at the radius of a row here, okay, at that particular point. All right, so the distance actually here, actually, this is a column, okay, so this is a row, right? The row, this row, you can see that row is going to be just the f of u, okay? Row is f of u, clear? Yeah. Yeah, the x coordinate of this point is so that's f of u. All right, so that is the distance. And that's just equal to rho, right? So from here, yeah, rho is positive. So that implies rho to the negative one FV is a unit vector. Okay, unit vector tangent to the circle. Tangent to the circle on this, tangent to the circle. Okay, so this is a sigma v. If we divide by the radius rho, and that's going to be the tangent vector. Okay, we know that sigma u dot, this is it's also going to 0, right? They're perpendicular, right? So, yeah, okay, that's what we know. Of course, if you want to talk about the first fundamental form, the first fundamental form depends how do you write it. Sometimes you just use a du, then and this is going to be e du square in the book, always like written in this form. That du dv n plus g dv square, and the e is 1. That is going to be 0. That's just f of u squared du square. Okay, and du is just a small element. Yeah. Okay, so that's the first fundamental form. Okay, that's all we needed to. That's all we needed to know. And in my last class, I used that, and with geodesics. Let's consider geodesics. Okay, so lat gamma. I'm going to use this gamma s, which is sigma us vs be a unit speed geodesic on this surface. Okay, and okay, so let's take a look at this. Now, using those coefficients, e equals 1, f equals 0, g equals 0, right? What do we got here? We got in the last class, I got 3 equations, geodesic equations that satisfy yeah, let me give you, let's recall what we got before. But we can redo the problem here. Okay. So geodesic, right? It is unit speed geodesic. So it can satisfy the following equations. Okay, let me write down, we E equals 1, right? and F is 0, so DDS U dot, okay, equals half of, okay, E is 1, F is 0, so G. So it's 2F and F prime V dot, okay, that's the first equation, okay, and then the second equation, F is 0, G is going to be F, right? Okay, so that is going to be, I think they're all equal to 0. So those are the two equations, simplified. Okay, so here U dot is DUDS, okay, V dot DVDS. Okay, now when there's a derivative with respect to arc length, I usually use a dot. Okay, so that's what we got. And we know that, we know from this, let's look at, we see that from here, we can quickly figure out some special geodesics, okay? Some special geodesics. So we can see that, let's see, meridians are all geodesics, okay? Let's stay to the first result. Okay. Every meridian is a geodesic. Okay, now let's prove this. So meridian, it means V equals a constant, right? Right, that's a geodesic. Using our parameterization, you will see that, so this is about equation, you let the V to be 0, right? Let's see what we can get. And that's going to be 0, okay? And the second equation is satisfied automatically because V dot is 0, right? So the second equation automatic. So this implies U is going to be AS plus B constant, right? Differential twice, and that is constant. So any such curve is a meridian, okay? So the gamma S, more precisely, is going to be f of AS plus B cosine V0, f of AS plus B sine V0, and G of AS plus B. It must be in this form. Okay. Now it is unit speed. Okay, unit speed means, if we already assume the unit speed, that means U dot square plus FU square V dot square should equal to 1. So that means actually here, A square is going to be 1. So A is going to be plus minus 1. Okay, so this A actually is a plus minus 1. Right, so we do get minus 1 is going the other direction, right? So this is yeah. So this is a geodesic, and is, yeah, this is the geodesic is meridian. Meridian, okay? Yeah, maybe it goes down, maybe it goes up. You know, this is different. So depends on sign. I think if we choose positive, it's going up. If we choose negative, it doesn't matter, right? Right, and here is this is the, okay. Second, a parallel, we call it a parallel. Right? A parallel U equals 1, okay, is the geodesic. If and only if that's going to be 0. All right, so to see that, now that means let's understand the geometry meaning of that. Remember the distance from that point to the axis, and that's the rho. Rho is going to be f of u, right? So that means as long as u0 is a critical number. So for example, when rho has a minimum value or maximum value, right? Those gives you a geodesic, okay? So so let's look at this first, okay? Before then I try to understand. So look at this equation, above equation, right? So when u is a constant, right? When u is a constant, the above equation is going to be when you use a constant dds, so that's going to be 0. Okay. Okay, right? So that's the equation. Okay, so let's try to solve it. You know, this is not never be 0, right? Because we use, that's our assumption. Yeah, to get the surface erosion. Okay, so this implies V dot is going to be, all right. Yeah, from the second equation, I'm trying to find the general, right? From the second equation, this will be a constant. And you plug into the first equation, and this is constant, so u dot square plus, right, f right, the unit speed. This is always the equation we have here. So this is going to be 0, right? Yeah, and that is, so we see that it's going to be plus minus. Now it depends on the value of f, yeah. So it's constant, right? It's not going to be 0. If it's not going to be 0, then the above equation implies f, that's going to be 0. Okay? All right, so so you will see that gamma s is going to be v dot is some constant. This is a parallel, okay? So this is a geodesic. Right, and there's a condition f prime is 0 is going to 0, okay? And there's a condition of this, okay? Is a geodesic with f prime. All right, so what is f, right? F, yeah, so this is our picture. So this is a axis, right? This row, let's call it row, is right. Row actually is just equal to F. Okay. So that means when rho is going to be 0, okay, rho, okay, F prime equals 0 if F has an extreme value, has a local maximum or local minimum value at some point. Okay, right? Because that's what we learned from calculus. So if I draw the picture, I can tell, okay, let's draw the picture of us some city, right? Yeah, let's look at this. Okay. This is a picture. This is a curve. So we, right? Okay. So this is surface. Now, when you look at this surface, some are interesting bottom, right? So you can tell immediately where's the geodesic. Horizontal parallels, right? From here, this is geodesic, right? Because look at the radius. The radius has a minimum value, and this one is also geodesic, and this probably is geodesic. So those are the geodesics. Besides the meridians, you can also find those geodesics. Okay. Good. All right. The question is, how do we? I think there was a French mathematician. Yeah, he make a further observation. Okay. He trying to understand the geodesics. How he's trying to characterize the geodesics in general. Okay. He claimed that. Okay. He claimed that if this is a unit speed curve on the surface, if it's geodesic, then this must be constant. Okay, so so that's my picture here. So this is a curve. I'm going to talk about this curve. Whether this curve, is a okay, this is gamma, right? So what I'm doing is, this is a meridian. Okay. I'm going to define this angle by phi. Okay, that was the angle here. Okay, tangent vector, if it's parallel, if the curve is parallel, then this angle is 90 degrees. They're perpendicular to each other. If this curve is a meridian, then phi is going to be 0. And that is the angle. So that angle depends on the function of S, right? Depends on location of the curve. Okay. So here's what he said. Okay. Let gamma be S, unit speed geodesic on S. Okay, this is surface of a relationship. Okay, the first statement is okay, if gamma is a geodesic, then rho times sine phi must be a constant. Why? So it's basically you get the answer here. Okay, so the geodesic cannot be arbitrary. Okay, and if this is a constant c, then you can tell that phi is going to be C over rho, you know, right? So how do you decide, how do you draw the picture, right? If you already, the geodesic already stop at the point, and you know the rho, right? So then you can determine in which direction the geodesic will go, because sine phi is going to be the constant C divided by rho. Okay. Okay, conversely, if rho sine phi is a constant, okay, and here's a condition, and no part of gamma is a part of some parallel. Then gamma is a geodesic. Okay. Now, if gamma is part of the parallel is already geodesic, right? So you can, yeah, when and under which condition? I think when so if some function, if some curve satisfies this condition, rho sine phi equals C. Okay, parallel means phi is always equal pi over 2, right? Okay, and then rho is a constant. All right, so how do we solve this problem? Okay, let's do some calculation. Okay. So this is a unit speed, right? So we know so unit speed means u dot square and f u square at v dot is going to be 0. That is an assumption. So now we take a look at, let's take a look at the gamma, right? Gamma s. So gamma dot s. You see we have a two unit vectors here. So this is a sigma u and sigma v and right, rho by rho. Okay. So I can describe, if this is a phi, right? Then I can describe cosine phi sigma u sine phi log to sigma, right? Because it's a two vectors. All right, so what does that tell you? Well, this is going to be sigma u dot, sigma v dot, right? So you get to the following identity. This two must be the same. Right? So V dot equals 0 receiving the sine V. Yeah, you see, rho is f of u, but f of u is also a function. Right? Phi is just depends on the function. Yes. So this is the identity. Now remember the geodesic, right? Geodesic equation. Now we have the three equations. I'm going to go back to write down the three equations. Okay, we have three equations, geodesic equation. Okay. Yeah, just if you use one dot, then f of u square 3 dot is going to be 0. So I'm interested in this case, right? That is one, right? And I multiply both sides by rho square. So what I got here is rho sine phi, right? That's the equation star equation. So equation double star implies okay. So that implies rho sine phi must be a constant. That's cool. So that's a necessary condition. Okay, the proof is pretty straightforward. Okay. Now, conversely, yeah, the second equation gave you this information. What I want to say that actually the second equation, those two equations, second equation implies the first equation. Okay, for surface erosion. How come? So we assume I now, right? Okay. So we have a curve, right? Satisfies this equation. I have a, we have to prove it's geodesic, right? According to his theorem, right? It's 1 and 2, right? For the first one, we already proved it, right? So this is it. But we from the above we have this identity. This is always we have this identity, regardless of whether it's geodesic or not. So that means rho square, right? It's constant. So So the derivative of rho square v dot is 0. Okay, i.e. So the second equation is satisfied. In order to prove it's geodesic, you have to prove the first one is satisfied too. All right, so how can I do that? Well, we haven't used an assumption. Yeah, this is a unit to speed. That's right. It's curve. So this assumption. Okay. By this assumption, I got u dot square is 1 minus f of u dot v dot square. Okay. So it's going to be we have this identity. So it's going to be rho square, and v is going to v dot is going to be 1 with this assumption, right? So when the constant c rho square and square. Okay, we're using this fact, but we already have this identity. Okay, so we get 1 minus c square rho square. That's good. Then I differentiate twice. Okay. Then I got negative. I think it's 2, rho to the negative 2 is rho to the negative 3. And the constant square, right? Okay, now what? I think we have another one here. Yeah, this is a low product, okay? Because this is a composite of two functions. When you differentiate rho, you get the low product, okay? Right? The derivative of s rho, that's inside, right? It's the rho prime u d dot, right? Okay, so now your DC, you take u out, minus 2 rho there's no 2 here. So u dot is going to be 0. Now we have to assume that u dot is not going to be 0 because no part is parallel. Okay, since no part of gamma is parallel, is a portion of a parallel. Okay, if u dot is going to be 0, on some small interval, then u is going to be a constant. And it's constant, then that is become portion of the parallel. Okay. So that implies u dot. Okay. So I can write this as this. Okay. But we already got C over rho is V. Like C over rho squared is V. So this is nothing here. F of u is F of u, F power u, and this is a V dot square. Okay, because V dot rho square is going to be constant. We already have this problem. So this is a second equation. Okay, this is a second equation. So basically, what we did here, yeah, therefore it is geodesic. Therefore it is geodesic because satisfying two equations. Right? Yeah, we under this this equation is pretty strong. Okay, so if we go back to this identity, these two equations, okay, these two equations actually what we prove here without using rho, okay, what we prove here is okay, those are the so f prime v dot square, okay, and ds so what I have proved that is if u dot is not going to be zero, then this dot also implies the first one. Okay, and using the fact you have to use this fact. That's an assumption. So those two equations are essentially the first one can be get rid of. Okay, if u dot is not going to be zero. What is u dot equal? When u dot equals zero, that is a parallel field. Right? Because u is a constant. Okay, so that's good. Okay, so that's what we got. Okay, here's a remark. This is just the calculus, nothing to do with geometry. Right? And u and v are related by this equation, that's unit speed. And then you have two different equations. You just prove that the second equation implies the first equation. So, but the second equation looks much simpler. Just f squared v dot is going to be zero. The geometric meaning f squared v dot is just the angle times f of u. Okay. Okay. Now let's take a look at the pseudosphere, the so-called pseudosphere. Okay. The pseudosphere is a sphere. It's kind of sphere, but it has constant curvature -1. Right. It's surface erosion. Okay. It's incomplete in the sense the geodesic, the meridian, does not have infinity, does not go to infinity. Okay, let's stop okay, somewhere. So if the geodesic, okay, so this is a uv, right? F of u cosine v, f of u sine v, and g of u. Okay, so f of u is going to be e to the u. Okay, g of u is going to be 1 minus e to 2u minus hyperbolic cosine e to the negative u. Okay, and you can check that always equal 1. Yeah, it's not easy to solve for g, right? If f is given. So the non-freedom for g, okay, once f is true. F is the explanation function, okay, e to the u, right? Let's understand the picture here, e to the u. And this is a x-axis, this y-axis, this z-axis. So the radius here, okay, the radius is e to the u. Then this is supposed to be 1, right? When u equals 0. It goes from negative to positive infinity. Okay, we have to assume that u is going to be, let's see. Yeah, there was a restriction here, right? So u is always a negative. Okay, u goes to negative infinity. So if I draw the picture, it's always below the yeah, anyway, so this is the surface. Let's continue. So when u equals 0, f of u is 1, right? Right? When u equals 0, that's the start point. F of u equals 1, right? And g of them is negative cosine hyperbolic 1. Which is going to be 0, right? Hyperbolic cosine 0 is 1, so that's why. All right, so the curve start from here somewhere, okay, on the in the space. Yeah, I have to move up a little bit. That's the origin. Yeah, when z equals 0. Yeah, that's the starting point. U equals 0, and it goes to negative infinity for going in that direction. All right. So you can describe the geodesic, right? The geodesic is going to be e. Okay, f of u is already given here. So let's try to describe the geodesics. Let gamma s be a geodesic. Then gamma s is going to be sigma us, right? So we will see that let's see. This is a surface. This will be the angle. then sine u. Okay. But still it's harder to understand, right? As you can see that, right? You know the angle phi, and you know what is the radius at that particular point. Radius is rho, and right, and u goes to negative infinity. So we're trying to find a new parameterization, and this is the parameterization original sigma, right? Yeah, I'm going to choose another parameterization. I let W is equal to negative U. Okay. If I do that, then e to the u is 1 of W, right? Okay, using this substitution, our u equals natural log of 1 of W. Now if u goes to negative infinity, to W u equals 0, that's equal, I think it's greater than 1. Okay. Right, since u is less than or equal to 0. Yeah, look at the UV plane, right? U is it's a v is from 0 to 2 pi. U is a negative, this part. And now you have a new transformation, and that is going to be W. Right? V is still it's 2 pi in this way. So W is greater than or equal to 1. Okay. Right. Now, if you use this substitution, what do you get? You will get, I'm going to use this WV, okay? That will be omega W cosine V, 1 over omega sine V. And this is also replaced by V. So it's 1 minus 1 over W squared minus half over cosine W. That would be the new parameterization. How it's related to the older one. Yeah, the older one. And it's going to be sigma. W is going to be natural. V is going to be natural log of 1 over W and the V. Okay. I believe that W should be less than equal. Should be greater than equal. All right. So with respect to this coordinate, okay, E tilde is going to be G tilde is going to be 1 over W squared. And F tilde is still 0. And the unit speed, W squared plus V dot squared is going to be unit speed curve if you use a W, right? It's going to be because of this, right? It's going to be W squared. Okay, that's WS VS via geodesic via unit speed. Let's say speed the curve first. Okay, so that's unit speed that would be, yeah, unit speed will be this equation. Okay. Now the geodesic, okay, it is a geodesic, right? Assuming gamma s is a geodesic. Okay. We know that rho sine phi is going to be constant in price, right? Right. It doesn't matter which coordinate you choose. Right. We prove that this is a curve. Here's a tangent vector. This is a meridian, tangent to the meridian. That's a phi. Okay, this is a rho, right? So rho times sine phi is going to be constant along the geodesic. Okay, and actually, this is going to be, let's see why this is true, okay? So this is because based on this coefficients, the geodesic equation, this implies this is actually is going to be equal to, okay. That is obtained from above, when we change the coordinate, right? We have, yeah, where's our equation here? Yeah, we have this identity. Okay, so but similar, right? We use this identity, even you change the variable, okay? You still have this similar equations. Okay? It's independent. If you change the x, change the different parameters, is still the same. Okay? So this is from the above equation. Right. All right, so now you have V dot equals CW squared. So there was a couple cases here. If C is a constant, right, we assume if C is a constant, and if C is zero, so if C is a zero, then that is a meridian. Gamma is a meridian. We are not interested in this case. So if C is not going to be zero, right? So what does that mean? Okay, I'm trying to solve it, but how can I solve it? Well, okay, well, we have an equation here. This is the equation, right? Combine that. Right, we have these two equations. Okay. We may be able to solve it. Okay. Let's see, what do we got? I put it here, right? So W dot square is going to be W square minus V dot square. And that is going to be V dot is a C W square and square. say I got W squared, 1 minus C W squared, right? All right, so you get an ODE, and you do get an ODE, then you probably can derive an equation. I'm not going to find the solution for W. What I'm trying to do is I find the equation dV dW. So V dot W dot. So here, what is a V? V is a CW squared. Okay. And what is a W dot? It's a plus minus W, 1 minus CW squared. So I cancel it. Okay. Okay, so I have a function, V depends on W, and I get rid of the parameter S, so there is a relationship between V and W actually, right? So then you integrate, and you will find out after you solve it, it's minus plus, I think it's 1 over C. It's 1 minus, yeah, that's a C squared. So this is a C squared, yeah. So 1 minus plus of this. Okay, what does that tell you? So both V and S, W can be function, right? So V minus A dot squared is going to be C squared, 1 minus C squared W squared. So it's going to be 1 over C squared minus W squared. So V minus 0 squared is plus W squared equal to 1 over C squared. It is a circle, right? So it is a circle. Yeah. So V WS, okay, and the VSS actually is a circle in the WV plane. Okay, now how can I describe the geodesics right now? Okay. So this is a pseudosphere. I have the map sigma tilde. Okay. Right, that's my W, that's my V. For a fixed I think for the fixed W, this will be as a circle here. Okay. Here's another one. The geodesic, okay, must be a circle. Okay, so what do we see that this is the equation circle, right? And a circle okay, square circle. So we have a geodesics. So the geodesic, what I'm trying to say that the geodesic can be described as an image of those circles. Yeah, and yeah, those are circles in the WV plane, right? So geodesics on the surface are the images of the curves. Okay. In the W viewplane. This is under the image sigma 2. Okay, so once the surface patch is given, we want to describe the geodesics on the plane, not on the surface. Okay, because geodesics are the images of the image and the surface patch. So what the equation you got is actually they are equations on U and V. So just sometimes you're lucky, you can get a general solution. Okay. In this particular case, a pseudosphere. Why we call it sphere? Well, it has constant curvature, but constant curvature -1. Okay. This is a kind of negative curved surface. So imagine our universal, for example, it's a 3-dimensional, maybe negative curved surface, but the curvature may be not constant. It's changed, but it's negative. And that means kind of the universe is kind of expanding. Okay, it's unbounded. Okay, you never reach to from mathematical point of view, you never reach to the boundary of the universe. Okay, it's interesting. Yeah. So I have to stop here, and we have a couple more lectures. I think we have 3 or 2 more lectures maybe. Yeah. Let's see. Yeah, I'm gonna